in the last class, we were looking at the frequency response of the common source amplifier. We did a lot of algebra and finally came up with this messy looking expression, and we are trying to make sense of the various terms. This of course makes sense that simply the response of the common source amplifier to at DC, and that's, as you very well know, it is minus GM times RL. We also recognize that even though there are 3 capacitors, the denominator polynomial is only second order, and that's because there is a capacitor loop. Finally, we are also happy that the denominator, all the coefficients of the denominator have the same sign, which means that the system is stable, right? And that means all this effort so far was worthwhile, because if this was not stable, then we might as well pack our bags and go home. Correct? All right. The next thing is that we looked at the numerator and we noticed that strangely there seems to be a 0, and the 0 happens to be in the right half plane. And yesterday we saw the intuition why 0 must occur, and that's because you can see that there are 2 paths from the input from that node Vx to the output, and whenever there are 2 paths, multiple paths from input to output, you always have some complex frequency at which the outputs of the 2 paths interfere destructively and therefore cause a null in the transfer function, right? And here you can see that the path gains are, one is through CGD, which attempts to pull the output voltage up, whereas the transconductance GM attempts to pull the voltage down, right? So we see that there is a 0, and because the signs of the 2 paths are opposite, it is now intuitively clear why you must have a right half plane 0. All right. Okay. So now it's the turn to look at the denominator, right? So at DC, of course, the denominator evaluates to 1 at slightly higher frequencies, right? So they're basically not DC, but not very high. Which of these 2 terms in the denominator do you think will dominate? Which term will dominate? Yeah. So the at low frequencies, therefore, the denominator will largely be determined by the constant and the S term, right? But the S square term will will only kick in at much higher frequencies, right? So let's now try and see if we can make any sense of why this term is there in the first place, and why it is of the form it is. So at low frequency, therefore, what does low frequency mean? What is the meaning of low frequency? Like anything else, right? There's low basically makes no sense unless it's compared. I mean, something is compared to something, right? So what is compared to what now? Okay, I mean, okay. Can we comment about the frequency dependent currents and the frequency independent currents? So you have various elements in this network. You have capacitors, resistors, and so on, right? At DC, all the current is flowing in the elements in the branches whose behavior is frequency independent, right? As you keep increasing frequency, what happens? Yeah. So basically, it will, as frequency keeps increasing, these capacitors which are open at DC start to draw current, right? So basically, low frequency. Another way of thinking about low frequency is basically the frequencies at which the capacitor currents are very small compared to the the currents in the frequency independent branches, right? In this case, resistors and the control source GMPX. Is this clear? All right. So if we can, at low frequencies, if we can neglect, to first order, if we can neglect the capacitor currents, what voltage? I mean, what is approximately what is Vx? Vx is approximately Vi. Okay, and what is VO? This is approximately minus GM RL times Vi. Okay. So, what comment can you make about the current through the capacitance? The voltage across the capacitor is Vi. So, what is the current through the capacitance? Yeah, I mean in the Laplace domain it is simply nothing but SCGS times correct, alright. So, what is the current through CGD? What is the voltage across CGD? Yeah, it's 1 plus GMRL times Vi. So, what comment can you make about the current through CGD? It's SCGD times 1 plus GMRL times Vi. All right. So, if you look at the impedance at DC, of course, the impedance looking here is infinity, right? But at the as frequency changes, I mean current is flowing. So, yeah, there is basically an impedance frequency dependent voltage to current relationship. And so, what is the I mean, so at low frequencies, therefore, what comment can we make about the impedance looking in? We have applied a voltage which is Vi. The current flowing is SCGS times Vi plus SCGD times 1 plus GMRL times Vi. So, this basically is the current. So, what is the impedance looking in? So, the impedance looking in therefore is 1 upon CGS plus CGD into 1 plus GMRL times S. So, what is this? What does this element look like? Are they in parallel or in series, man? Okay, C1 plus C2. Okay. So, you basically so it looking in, therefore, it looks like a capacitance of CGS by 1 plus CG. I mean CGS plus CGD times 1 plus GMRL. So, what comment can you make about the transfer function from Vi? Okay, we know that this is only approximate. All right. So, what is it? What will be the a better approximation to that voltage there? The looking in impedance here. So, basically, this is Vi, this is Rs. Looking in here is a capacitance of value CGS plus CGD times 1 plus GMR. So, what comment can you make about the voltage here now? Yeah, this voltage, that voltage, that Vi is was a zeroth order approximation. To a better approximation to the voltage there is, which is valid at low frequency, must therefore be Vx of S must be nothing but, or Vx by Vi is nothing but 1 over 1 plus S times Rs times CGS plus CGD times 1 plus GM RL. Now, so that is the Vx. So, now we are interested in finding, I mean, of course, at DC the output voltage is minus GMRL times Vi, but we are interested in finding the voltage at, I mean, the transfer function there at low frequencies, correct? Okay, not at DC, but slightly removed from DC. Okay, and that is simply the transfer function. I mean, we know the transfer function from Vi to Vx is this. We now therefore need to find the transfer function between Vx and V0, right? So, if we know the transfer function from Vx to V0, then you multiply the two transfer functions and therefore you will be able to get Vi to V0. Is that clear? If you have a network, if you know this voltage, you can remove the entire portion to the left and replace it by a voltage source Vx, correct? And that's a voltage source. So, the fact that you are drawing current from that voltage source does not affect the transfer function from Vx to Vo, right? And we have already accounted for the current flowing through CGD. That's already coming in here. Is this clear? So, basically all that we are doing is we are replacing, if you want to look at it that way. Let us assume we have Vx here and you have CGD, this is GM Vx, this is RL and this is CD. This is the circuit we are analyzing, correct? We know Vx already. How do we know Vx? Because we have accounted for the loading of the rest of the circuit following that Vx node, correct? So this is what we are trying to find, Vx by, Vo by Vx, alright. So, again what do you call the first order approximation is you have GM Vx being what do you call pulling current out like this, okay. And so what comment can we make about the time constant across RL now? Which is larger, this Vx or minus GM RL Vx? Minus GM RL Vx is a much larger voltage than Vx. So, for all practical purposes therefore, what comment can you make about this voltage? It is very small compared to this voltage, correct? This is swinging a lot, this is not, this is all swinging very little, right? So, what comment can we make about the time constant across across the capacitor across the capacitor CDB? Or in other words, what will be the, first of all, how many, if you find the transfer function from Vx to Vo, what do you expect to see? What order do we expect to see? First order, why? If you want to find the transfer function, what is the order of the system? Yesterday we discussed that the order of the system is independent of where the input is connected, right? So, if we, the denominator polynomial of this transfer function should be independent of Vx, right? So, if you short Vx, you will get, you should get the, it does not matter where you put Vx. So, what comment can you make about the denominator polynomial of this? Of course, you can evaluate it, but what I am asking is what comment can we make about the denominator polynomial? What order will it be? So, basically, if you set Vx to 0, this becomes a short circuit, GM Vx becomes open, right. So, basically, you have the time constant that the circuit is associated with, therefore, is RL times CDB plus CGD, right. So, therefore, Vo by Vx must therefore be equal to the denominator polynomial must be 1 plus SRL upon CDB plus CG, correct. And do we expect to see a numerator or do we expect to see a numerator polynomial or no? Yes, why? So, from Vx to V0 there is a path through CGD and from Vx to V0 there is another path through GM, right. So, basically you expect to see a numerator polynomial. So, what will this be? What will the DC gain be? Minus GMRL, and you will have a right half plane 1 minus S GM by CG, correct. So, basically this is telling you that if this was driven by a perfect voltage source Vx, oh sorry, thank you, SCGD over GM, yeah. So, this is just telling you that if this was a voltage source Vx, the transfer function from Vx to Vo is simply this character. And is this approximate or is this exact? This is exact, right? There is no approximation here at all. The only approximation is coming because of input to Vx is approximated because of we said that at low frequency, well, the output is approximately minus GMRL and so on. So at low frequency, therefore, VO by Vi is approximately what? Minus GMRL times 1 minus SCGD by GM over 1 plus S times let me call that S by P1 . Okay, and this is 1 plus S over P2. All right. So you can see therefore that which is approximately for small s, this is what? Minus GMRL times 1 over SCGD by GM divided by 1 plus S into 1 over P1 plus 1 over P2. Okay. And what is 1 over P1? This is time constant associated with at node Vx, and this is the time constant associated with at V. All right. So basically, I mean, and of course, there is a Z. All right. So this is a good approximation to the frequency response at low frequency. So what is the so therefore we see clearly that we of course get the DC gain and the 0, and at low frequency the denominator polynomial must look like this. So what is this 1 by P1? What is the time constant at node Vx? Well, that corresponds to charging the effective capacitance here, right, through a resistor Rs. So what is the time constant there? What is the effective capacitance at that node Vx? It's I mean, it is kind of tempting to think of it as just CGS plus CGD, but it is not. It is more than CGD. Why? I mean, so if you have a capacitor C and you apply a voltage V, correct? The looking in capacitance is obviously the current flowing is S times C times V. But if this is moving in the opposite direction, as if this voltage is minus AV, correct? So this voltage is only moving by V, but the other plate of the capacitor somehow is going down A times the net voltage across the capacitance, even though you have applied only V, is 1 plus A times V. All right. So this capacitance C, when looking in here, appears as if it has been multiplied by a factor 1 plus A, right? And this is often what is called the Miller effect, or this is called Miller multiplication. All right. So this is an example of the evidence of Miller multiplication. So CGD is Miller multiplied right. So that the effective capacitance that you see looking in is not CGS plus CGD, but CGS plus 1 plus GMRL times CG. And therefore, the time constant associated with that first node is nothing but Rs times the effective capacitance, which is CGS plus CGD times 1 plus GMRL times RS, that is the time constant at that node. What is the time constant at the second node? It is nothing but, what is it? RL times CDB plus CGD. So, that is the time constant at the second. Alright. So, basically you can see that the first two terms make sense, right. There is intuition behind why these terms look like the way they. Alright. So, the last term, of course, you know, have no great intuition to offer, right. It basically, you know, I mean, this is what now I would call think like how you do in gate, right. This coefficient must have dimensions of time square, right. So, it must be, you know, multiply 2 resistors and 2 capacitors, right. Your coaching class forgot to tell you which 2 capacitors. So, you could be you do not be partial to anyone, you just basically take all the 3 capacitors and then multiply them up 2 at a time, right, and then you see only 2 resistors in the picture. So, that is RS and R. Okay. All right. So, what do you call so that is so now when you see a picture like this, I mean, you know, you should be able to simply write out the transfer function, right, without having to sit and rewrite solve all the KCL KVL equations, you know, all over again. Okay. So, the key point therefore is that you know, if you drive the common source amplifier with a resistance you know, RS, then if you want to approximate the common source response by a first order system, then to a very first order, you can basically see that the CGD over GM, right. What comment can you make you know, when you compare it to the denominator pole, the numerator, which will be much larger, this time constant in the denominator or this time constant? You know that GMRL is much larger than 1. So, what comment can you make about the time constant here versus the time constant there? Which will be larger? I mean, CGD over GM or this monster expression in the denominator? The denominator is expected to be much larger, correct? And as a consequence, therefore, you know, if you want to approximate, you know, the frequency response of a common source amplifier to first order, you can, you know, safely say that this is minus GMRL divided by 1 plus omega naught, where omega naught is 1 over simply the sum of the time constants, which is RS times CGS plus 1 plus GMRL CGD plus RL times CGD plus CD. All right. In many cases, you know, the load that you will see is not purely a resistor. You also, let's say you are trying to load another amplifier, then its input capacitance also becomes a part of CDB, correct. So, basically you will see that you know, right, where the bandwidth is dependent on you know, RS, RL, and yes, basically this is the time constant sum of the effective bandwidth is basically the sum of the reciprocal of the sum of the time constant. So, basically the bandwidth is simply inversely proportional to, you find all the time constants everywhere, you add them all up, right, to first order. It's the bandwidth of the system is simply 1 over GM 1 over tau 1 plus tau 2, where tau 1 and tau 2 are the time constants. Okay. All right. So, this covers the common source amplifier, but we will be coming back to the full blown expression later when we cover two-stage op amps. So, it's important to be aware of there. We are not going to sit and rederive the expression all over again. We should now be in a position to simply write out the expression, because most of these terms are pretty self-explanatory, or we have some way of remembering. All right. So, that was the common source amplifier.